There. So today we're going to be doing Layer 3 VPN scaling and internet access. So when we talk about scaling, what do we mean? Well, so far we've seen that we can create a Layer 3 VPN. We can create that between customer sites, and we set up our CE sites, our customer edge routers, customer edge sites, and we've then set up our routing, our CE and our PE, and we've seen how we can then create a VPN between those two CE sites. So that's fantastic. We know we can do it. So the issue is, how many can we do? How many of these types of VPNs can we put in place? And one of the issues with it is that you can begin to overload your PE routers, because the PE routers, let's just say we've got one site connected, that's all good. What about 2 sites? What about 3 sites? What about 50 sites? Okay, what happens then? So what we're finding is that the PE routers are maintaining these VPN routing and forwarding tables, and they maintain a separate table for each and every site. They also then have to advertise routes to their peers and receive routes from their peers. So they therefore then maintain a peering arrangement, peering with BGP peer, with all the other PE routers on the network. And so because of the volume of routes that are sent from every site between all the PE routers, the PE routers are quite busy. Okay? There is a limit. It's fairly high, but there is a limit to just how many routes a particular router can handle. Now, it can be extremely high, but still there is a limit, okay, depending on the volume of traffic, depending on a number of things in actual fact, as to just how many you can do. So what we're looking at today is we're going to look at how can we use these Layer 3 VPNs, and how can we set things up so that we can run many of these in a provider's network. I mean, from the provider's perspective, it's all about what services can the provider deliver, because this is their business, right? They are in the business of providing connectivity. So the goal of a service provider is to be able to provide these services and charge for these services. So you don't want to hit this limit where, oh, well, that's it, you can't do any more. You want to be able to sort of keep going with it and provide these services to as many customers as possible. So we're looking at scaling. How can we expand this? How can we grow this to as many as possible? So we're going to sort of cover a few topics here today around this. We're going to look at a few things as 4 ways really to improve the scaling. How can we grow our VPNs? Then we're going to look at how do we provide our customers our VPN customers with internet access as well as VPN. So scaling Layer 3. Now there's an RFC which does talk about that, and there's some recommendations in there. So observe PE router limits regarding total number of routes. Now that can be quite high. Keep the CE to PE routing simple, and then create multiple BGP route reflectors for VPN routes. We're going to look at this route reflector idea in a bit more detail, because the thing, we're going to do a lab. We're going to be doing a lab on this after we go through and look at these things. So we're doing this labbing class, and the lab involves using route reflectors. So the thing is that this particular course, this MPLS course, doesn't actually explain route reflectors at all. I just kind of assume you know what they are, which of course you don't. So what we're going to do is we'll take a look at route reflectors. There's a really great learning bite that is included on the learning board that explains route reflectors very well. So I'm just going to sort of use that learning bite there's some great diagrams in there. I'm going to use that learning bite and I'll just go through it and explain the concept of a route reflector. But a route reflector is not something that is only used in the context of VPNs. It is used more generally in service provider networks to overcome some BGP limitations. So we'll look at that and just go through and take a look at how that works. There is a BGP feature called refresh, which is supported in our infrastructure here. We'll look at that. And we can use also a thing called route target filtering, which minimizes the amount of routes that have to be sent, the amount of route advertisements that have to be sent by BGP routers and processed by the PE routers. So if we can limit how much route advertisements have to be sent, we can ultimately run more VPNs. Okay, so we're going to look at these things here. So these are, as we've already discovered, P routers that are involved in the transit traffic really don't need to know anything at all about the VPN. We use two levels of labels, an outer label and an inner label. We looked at that last week when we actually looked at how our layer VPNs were set up. The outer label is used for the VPN to transit across the provider's core network, so from PE to PE. And what we discovered is that we use penultimate hopping, so that the last P router along the path will pop the label, and then the packet will arrive at the PE router with just its inner label, the last label. And what that label does is it references, or within the routing table of the PE, the next hop for that particular label value is the interface that is associated with the particular CE site that VPN is associated with. So that's that inner label that actually connects the LSP to the customer site. It's that inner label. The outer label just gets transited through the provider's network. So we looked at how that sort of worked last week, looked at how the BGP signaling actually sets up the inner label value, and that label is then pushed onto packets and then arrives at the other end and is eventually popped by the P. So looked at how all that worked. So we have these two labels, which very efficiently means that we don't really need the PE to know anything about the VPN at all. The other thing that makes this a very efficient process is the second point, where the PE router only maintains routes for the sites that it is servicing. So if it's servicing 5 customer sites, it maintains routes for just those particular customers and those particular sites. What that means is that if a customer adds another site, or we take on another customer, that we don't have to go and reconfigure all the PE routers in the network to know about those. We only configure just one router that is connected, or just the routers that are connected to the sites themselves. Because BGP, our MP BGP, will actually handle the transfer of routes between the PE routers, and so really You don't have to configure the whole network. Only got to configure just the PE routers that are connected to the sites themselves, and then which means that there's less work. That's the bottom line. Okay, there's less work to do to aid customers or to change customers change sites, add sites, move sites, etc. There's less work to do from an administrative point of view to maintain this infrastructure. Okay, so now we're going to get to the next point, which is route reflectors, and we want to sort of get into what they are and how they work. Just explain what is this thing, what a route reflector. What it gives you is that not only can we have a route reflector, but we can partition this route reflector to divide the workload of the various VPNs between different route reflectors. So route reflector is just a router, basically. It's a BGP speaking router that functions in a particular way that provides an efficiency for us in the way BGP works. So we'll get into that in a bit of detail. Explain that. So we end up with no single component in the system is required to maintain all the routes for the VPNs. One of the other things we get to do with route reflectors is we can also eliminate single points of failure within our network by having multiple route reflectors share the same workload. So if something fails, we don't lose connectivity. So what we end up with is our goal is the capacity of the system not bound by the capacity of a single component. So we end up with a router reaching its maximum number of routes, or we just can't add any more to it. So what we can do is you can offload that to another device in your system. So you can keep, what the point is, you keep growing this, okay, and keep adding more customers and being able to provide more services, which is the business of the internet service provider with carriage. Okay, so it's about supporting that business model, allowing the services to be properly delivered to the customers, so that service provider can actually go ahead and expand, operate, and grow their business. So that's the goal. That's what the technology. The goal of the technology is to support the business of the service provider. That's what this is about. All right. So let's take a look at where we're going here. So scalability, VPN Pacific route reflectors. So here we've got this PE device sitting there, and then we've got these two P routers there, and we're calling them VPN RR, which is just abbreviation for route reflector. And what we're saying here is, well, some of the VPNs are going to be handled by one of the route reflectors, so that's VPN from 1 through to 99, and there's another 100 that are going to be handled by another route reflector. Okay, so what I wanted to do though is, since we are in here talking about route reflectors, I just wanted to get in and describe just exactly what are route reflectors. And I just want to go back, and I'm actually going to use this really great learning byte. Just going to put that up on the screen there. So this is great, this learning byte that is included in your MPLS course. And it first of all starts off with the point of why do we even need a route reflector in the first place, and it comes back to the way that BGP works. So this is a standard kind of IBGP setup, where the way that IGP works is that you set up a full mesh between all your IGP routers. So here we've got five routers, five IBGP peers there. So let's just imagine that, well, this is one autonomous system. Let's just imagine that outside of this autonomous system we had an eBGP peer. Okay, so what the way that BGP works is that if any of these five routers receive a route advertisement from a eBGP peer, And let's face it, that's where all the routes come from. They come from one autonomous system into another. Otherwise, if they don't, then we've got some kind of export policy exporting the routes into the BGP routers themselves. So they are either coming from outside or they're originated, from within the AS. So there are two possibilities. So let's just say they're coming from the outside, and let's just say that this one of these iBGP routers receives this route advertisement from its eBGP peer. Well, how does BGP work when that happens? What is the default behavior of BGP? Well, that iBGP router will advertise that route to its iBGP peers. Okay. Now let's just say, for example, we only had one peer set up. Instead of a full mesh, we had the router only peering with one other route. Okay, what would happen? Well, that route would be advertised to the iBGP peer. Very good, that's what we want. But the issue is this: iBGP routers do not re-advertise iBGP received routes. So if a BGP router receives a route from an iBGP peer, it doesn't re-advertise it to other iBGP peers. And that's just how BGP works. And the reason that it doesn't is because when you have the iBGP, when the iBGP peer advertises the eBGP route to its peer, it doesn't add the autonomous system number to the advertisement. Unlike eBGP advertisements, which always add the autonomous system number to the advertisement. But iBGP advertisements don't add the autonomous system number. And the thing that one of the purposes of the autonomous system number being added to the route is that you can easily detect routing loops. Okay, so that if a BGP router is going to advertise a route to another BGP peer, and it looks at the autonomous system of its peer, and it looks in the route that it's going to advertise, and it finds that same autonomous system already in the path statement of the route, it doesn't re-advertise it into that peer. Because if it did, what that's saying, the fact that the autonomous system appears in the route statement tells that router that route has already been through that autonomous system. In other words, that autonomous system has in the past re-advertised that route, and now we're about to re-advertise back into that same autonomous system. So what we're doing is we're advertising the route around it and around and around. And we don't want to do that. So it doesn't do it. So the purpose of one of the purposes of the path statement is to avoid routing loops, but the other one is route selection itself. The shorter the path, the better. So one of the purposes is to avoid loops. So because iBGP peers never add the path statement when they advertise the route, there is no mechanism to avoid loops within the autonomous system because we don't have a path statement. So they don't re-advertise the routes to their other peers. That's just how iBGP works. So an IGP received route will never be re-advertised to an IGP peer. So if we only peer, so let's just say we had one router peering with another router, then the other routers that are in the autonomous system would never learn about those routes because they would never be re-advertised to the iBGP peer. So the only way for all of the IGP routers to be aware of routes that have been advertised by an IGP peer is to have a full mesh so that each router advertises all of its routes to every other router. Okay? So what you end up with is having a lot of peering arrangements. Now we've only got 5 there, but what if you had a really big network? What if you had 100? Okay, what if you had 100? Well then every one of those 100 routers would have to have a BGP peer with every other router. That's a lot of peering. Okay? You add one router you've got to go and figure 100, all right, to maintain that. So not only is it bandwidth intensive, processor intensive, but it's admin intensive as well. All right, so this is a limitation of BGPs. It's a service provider problem, okay? Because it's really the service provider that are operating BGP. No one else does that, at least much. So it's really a service provider problem to have this scale of BGP, this number of routers, and to end up with this problem. So the solution is to have a route reflector. So let's just flick through to the diagram about that. I'm just going to kind of flick through a couple here, and we'll go there. Okay, so this is a diagram of route reflector. So what we do with the route reflector is you configure specific BGP routers to be route reflectors, and the behavior of route reflectors is different from the default behavior of an iBGP peer, in that a route reflector does re-advertise iBGP receive routes. So when you configure a router to be a route reflector and receive routes from its peers, it will re-advertise those routes. So let's just say we're over here on the left-hand side of this diagram with this very top router up here, this top client router, advertises down to RR1. RR1 will re-advertise that back to the other two clients, but it will also advertise it out to RR2 and RR3, and RR2 and RR3 will re-advertise that out to its clients. Okay, so what we've achieved here is we've avoided having to have a full mesh of BGP by configuring certain routers to become route reflectors. So we've solved the problem, we've solved the full mesh problem for the service provider. There's a few other bits and pieces that we do here I mean, we've still got this possibility of, we've still got this routing loop possibility that we create by not having the pass statement in there. So if we go through and take a look at this, here's our router advertising our route. It gets re-advertised to all of our peers. Okay, so one of the problems that could occur is that R2 could advertise that down to R3, and potentially R3 could advertise that all the way back to RR1. Sorry, RR1. So we could potentially still have this routing loop in here unless we do something about it. And really, the thing that we do to avoid it is we create this extra attribute called a cluster ID. So a route reflector is configured with a cluster, and the clients that appear with that route reflector are part of that cluster. So every route reflector has got a cluster ID, and the cluster ID performs the same job as the path statement does for eBGP routes. So the cluster ID is kind of like for iBGP what the path statement is for eBGP, in that the routers, the route reflectors, don't advertise routes back into the same cluster that they received it from. Okay, so that avoids this loop. So what will happen is that RR1 will advertise it out to RR2 and RR3, but RR2 and RR3 won't re-advertise that back to RR1. Okay, it won't come back. And in fact, if we give RR3 the same cluster number as we gave RR1, then R2 won't even advertise it back to RR3 at all. So the goal is really that these clients out here on the perimeter of a network receive the routes. Okay, that's really our goal. So, and the route reflector takes care of that for us and does it for us. So that is really the concept of a route reflector. They're used in provider networks that they don't are not necessarily associated with VPNs. They're used even in a non-VPN environment. This environment could be a non-VPN environment. It just overcomes that whole meshing, that whole mesh of BGP that creates a problem. Let's just go and take a look. There's a configuration example over here. We just want to take a look at that. Yes, thanks. It was that one and that one. Thanks. I'm going to get on to the next slide here. There we are. That's what we're looking for. So this is the configuration that this is how you create a route reflector. We're in edit protocol BGP. We've got a group here, internal peers. The type is internal. We've got a local address, which is our local loopback address. Then we have this cluster statement right here. And the number after the cluster statement is the cluster ID. It is fairly usual to use the loopback address of the route reflector as the cluster ID. And then you've got these three neighbors here. They are our clients. So in a route reflector situation, you have routers which are considered to be clients of the route reflector. It's these three right here. They are the clients of this particular route reflector. So that's the configuration. It is this configuration that makes this router a route reflector. Okay, apply that configuration. It's now a route reflector, which means that the default IBGP rules no longer apply. You haven't got to change any policies or anything, just that alone will do it. And it will now re-advertise its IBGP received routes to its clients down here, these neighbors. And we'll also advertise to other route reflectors that it's here with as well. So there will be other groups besides this group, other groups that will peer it with other route reflectors. Okay. So that's just other BGP peering groups will be there. Okay, so that's essentially, that's really what I wanted to cover as far as the route reflector thing goes. Okay, so it's a pretty standard service provider mechanism to overcome the need for a full mesh of IBGP peers. All right, so. And actually, when we do our labs, we'll go and take a look at. We actually do set up. We set up this arrangement with a route reflector. I want to go and take a look at that route reflector as well. Okay, so what we're saying is that when it comes to VPNs, we have what we can actually do is we can set up more than one route reflector for our little group here, our PEs, our PE groups. We can have a number of PEs associated with a particular route reflector, and what we can do with that, one or more. This diagram just got one, just PE1. What we can do with that is we can offload part of certain VPNs to one route reflector and other VPNs to another route reflector. Why are we doing that? So we just don't overload our route reflectors. That's basically what we're doing. It's sort of spreading the load. So any of these P routers can actually become a route reflector. I mean, it's possible for a PE router to become a route reflector as well, but it really wouldn't make any sense to do that because the whole goal is to offload sort of the load of all this over onto a non-PE router. The PE routers are the ones that are carrying all the load of the VPN. So we want to offload that. So what you typically do is you choose a P router that is within the same physical topology, so maybe it's in the same site as the PE routers that become the clients of route reflectors. So what we're saying is you can have more than one route reflector and you can offload certain routes or certain VPNs to each of those route reflectors to share a load. Okay. So normally you'll note here, looking at one of their P routers, not in the forwarding plane, so they don't require VRF tables. They have to support family INET VPN, and they've got to have LSPs back to the PE, just so that the next hop becomes a reachable next hop. Why is that important? Well, route reflectors are going to be re-advertising these routes, which means that the next hop has to be reachable. If the next hop's not reachable, the route will not be advertised. So just to achieve the goal of the route reflector, which is to re-advertise the route, the next hops to those routes must be reachable from the route reflector. Okay, and the routes are kept in the BGP L3 VPN table on the route reflector. Okay, so we're just talking about scalability and sort of the types of things that we can do. Okay, still talking about route reflectors. It doesn't need the VRF tables to be configured. All the routes are just kept in the, if you looked at the previous slide back here, they're kept down here in the BGP L3 VPN.0 table. So we don't need VRF tables on the route reflectors. It has to support the INET VPN capability and the activating the routes requires LSPs from a route reflector to the PE routers. So we actually achieve those LSPs very simply by creating LDP signaled LSPs on our provider core. So you may remember that with LDP signaling, what LDP does is it creates a level switch path between every possible link. So basically it creates a full mesh of LSPs. So that's what LDP does. It creates a full mesh of LSPs if you go and configure it on all your routers. And you end up therefore with a level switch path back to the PE. Alright, that doesn't prevent you at all from still using RSVP signaled LSPs for your site-to-site VPNs. You can run RSVP signaled VPNs in conjunction with LDP signaled VPNs. You may recall that RSVP signaled VPNs have a lower preference value than LDP, so that they will always become a preferred route to a destination. So the traffic, so even though there may be LDP, or there will be LDP signal VPNs between your PEs, if you go and set up an RSVP signal VPN, the RSVP signal VPN will become the next one because it has a lower preference than LDP. Okay. So yes, you can use both together. And you can still have your RSVP signal ones becoming the actual LSP that serves that VPN. Okay, so the PE routers filter receive routes based on route target. So we did look at that as well last week, and what we discovered that the purpose of the route target is that when the route is received by the PE, there is an import policy. Well, we can create an import policy. There's actually a simple way of doing it by simply configuring this route target statement within BGP itself. And what happens then is there is a route target applied onto as an attribute of the BGP route. So when when PE3 advertises the route up to the route reflector re-advertises the route back down to PE1. One of the attributes of the route is a thing called a route target, and the router can filter the imports on those route targets. And the purpose of that is to make sure that the routes are imported into the correct VPN routing and forwarding table for a particular VPN for a particular site. Okay, so really when we did this last week, let's just kind of rehashing what we did last week. So last week we saw how all that happened, how those route targets were used to filter routes and make sure that they were imported into the correct customer's table, routing table. Okay, so that's PE routers will filter based on that. Okay, so in this diagram here, we have got these yellow lines here being our route reflector LSPs, reds being our unidirectional LSPs, which probably are RSVP signaled LSPs there, and we've got our peering, NVDP peering between our P devices and our route reflectors. So we don't have a full mesh. Basically, the route reflectors are avoiding that necessity. Okay, so what we're talking about here is how do we scale this, how do we make this more efficient. These are just the mechanisms that we're using. We're going to do a lab on this, so we'll see it all working. Okay, BGP. So talking about BGP, you notice there's a lot of BGP in MPLS, right? So BGP, it's a stateful protocol. This is another problem that we want to solve here. Okay, so again, it's just the way BGP works, and the way that it works by default creates a problem for us when we're running VPNs. Let's take a look at the default behavior here. So BGP is a stateful protocol. Once peers are synchronized, they do not exchange routes again until a change occurs or the session is interrupted. So a PE router, just say for example, a PE router has filtered the route exchange with the route reflector VPN to limit the number of routes it maintains. The router adds deletes the VPN, which requires an update in the BGP table. The problem here is that if something changes within our VPN, we need some way for the PE router to get a route update so that it can refresh those routes or reinstate the routes that may have changed. And the issue is that by default, BGP will never send an update because it doesn't have to. So this BGP route refresh function allows a PE router to obtain routes for a new VPN without having to terminate the whole session or disrupt the VPN in any way, or the BGP sessions in any way. Okay, so this is just a feature, the route refresh feature, that is used to achieve that. So really, there's a few BGP issues that we have workarounds for that that are specific to the way that our VPNs work. Okay, let's take a look at this concept of route target filtering. Now we already know that we use the route target to import routes into a specific VRF table, but we can also extend the use of these to control what routes are advertised from the route reflectors. So by default, the PE router receives an update consisting of every route that the route reflector knows about. So it will just advertise all of its routes down to PE. That's the default behavior. And then what the PE does is it will then filter those routes based on the route target, and it will install the routes that match route targets into the VRF tables, and the ones that don't match it will just ignore. Okay, so it just drops the routes that don't match. However, we can kind of optimize that behavior and by using these route target filtering, in which the PE router will send a list of the routes that it wants. So it'll say, these are the route targets that I'm interested in, send that list to the route reflector, and then the route reflector will only send those routes to the PE router. So instead of sending absolutely everything, which then, half of it gets dropped or a lot of it gets dropped, we end up with the PE router saying, hey, these are the ones I'm interested in, and then the route reflector will advertise only those to that particular PE. So it's more efficient. So we're talking about how to scale, how to get efficiencies into the network here. Got a configuration here as to how that works. We will do a lab on this, and we'll go ahead and set up these route targets. You'll see how they work. Okay. This is our route target filtering, and down here we've got our route target set up there on our route reflector there with this route target set up. So what we're saying is that this particular route reflector is able to receive these route target requests from the PE router. So that's the configuration on the route reflector right there. So this is the actual route advertisements now that we've actually got on our PE. So we do a BGP summary. We see that we've got the BGP target parameter as part of our BGP session. So that really means that this router is capable of filtering its route advertisements based on route targets. This is the routes that it is receiving. So it's actually receiving a BGP route target route, and that has a list of route targets that the particular PE is interested in. This is our route target table. Let's go back to there. Route target table. This is a configuration on our PE now to cause it to put all of its received routes into its BGP L3 layer 3 VPN table. Which it needs to do, and we can add traffic engineering to that as well, and we can use LDP signaled LSPs in conjunction with RSVP signaled LSPs. And one of the comments around this is that not all vendors support RSVP signaled LSPs on the PE routers. Some vendors don't allow an RSVP signaled LSP to go from PE straight through to PE. They only allow LDP signaled LSPs to go to the PE router. So there is a workaround for that as well, if that's the situation that exists within a particular service provider's network. And essentially what we end up with is 3 levels of labels. Sorry, we have the outer RSVP label, we have an LDP label, and then the inner label, which is the VPN label itself, to identify the exit interface. Okay, and there's the configuration to achieve that as well. Okay, so there's lots of workarounds to solve kind of problems and so on that you may have to deal with. Okay, let's talk about what happens if something changes within our customer networks. So we have a VPN VRF table is added or removed from a PE router. Is it disruptive? No, it is not disruptive at all, because it doesn't disrupt our BGP peering in any way. How many router configurations must be changed when you add or remove a VPN table? Well, only the particular PE router that is associated with that customer site. So in this case, to peer with a route reflector responsible for a new VPN, we'll set that up. When a VPN is completely removed from a PE router, it simply withdraws those particular routes, and we can just do a route target filtering and route refresh to simplify that process. So we know we don't have to disrupt the BGP peering at all. Okay, the number of VRF tables is also a scaling issue. How many tables can you actually have? Well, it depends on the router and the device that you're running, maybe up to 9,000. Depending on the routing engine, number of total routes per device can vary, depending on a lot of things. Juniper's MX960s can handle up to 1.5 million routes, and can go up to 2.4 million routes with some of the processors that are available. So there's a few things that affect exactly how many you can have, and those factors are: does the PE router carry internet routes? So that's a thing as well. Most providers don't allow the PE routers to carry routing tables or general internet routing tables. They simply have a static default route to one of the P routers that will carry the internet routing tables. The other factor is, are the CE routing protocols stable? So are we flapping? Are the routes flapping? Are there problems within the CE? Because that will really cause a big load on the PE routers. One of the solutions there is to simply have a static routes set up between the PEs and the CEs, and that just avoids the whole overhead of having to run a routing protocol between the PE and the CE. You might recall last week we did a lab on that, where we just set up static routes. We had a default route from the CE back to the PE, and we had a number of static routes from the PE going back to each of the networks that were set up within the CE site. So static routing is obviously very stable, and takes the burden away from the PE of having to maintain another routing instance with the CE. The other factor is the PE router performing value-added services such as rate limiting and firewall. So that's just another load on the PE. So they're all the factors that will contribute to exactly how many sites you can have associated with a particular PE router. Alrighty, the other thing that we're going to take a look at is public internet access options. So how does the customer get access to the internet? Well, there's a few kind of ways around that. There's an RFC there, 4364, that talks about those three options. First option is that the PE router doesn't have anything to do with the internet routing at all, so the customer site simply has a completely different connection to the internet. So it has a specific route to the VPN, to the PE router, and then it would have a default route heading out to the public internet. So that's one way of handling it, pretty simple way of handling it. The other option is that the PE router performs redistribution between the VRF tables in the main instance while matching packets against both tables. So the PE router provides internet access. And the other option is that there is a central CE device sends internet default routes to a remote site. So the consequence of that is that all of the CE sites, the custom sites, access the internet via the VPN, which sends all internet traffic to a central CE site that has internet access. That's the other way of doing it. So there's three ways of doing it, and different configuration to set up those three ways. There's the first one, separate connection altogether. And the other way is that the service provider provides internet access via the PE. So there's some configuration around that. We'll actually do a lab on that. And the other one is that the sorry, we're still on the second one. So on the The other option is that there is one central CE that through which all of the internet traffic for that particular customer goes. That's the other way. We're going to do a lab on that second option. All right, so really what we were just talking about here is these internet access options. So we can have internet access not through a VRF at all, so the PE router doesn't get involved in that. The other option is that the PE router does get involved in that. So it goes through the PE router, and we set up route redistribution between the different tables, etc. And we'll take a look at that. And the other option is that there is one CE site through which all of the customer's traffic goes through to access the internet. All right, so the main focus of this chapter was scaling and how to achieve scaling of our VPN. So how do we expand our VPNs? How do we get more of them without overloading any single component? And we did have a look at the way that we can provide internet access for VPN customers as well. All right, so what we're going to do after this, there's some review questions, look at those. So basically, 4 methods to improve layer 3 scaling. So the things that we looked at is looked at route reflectors, looked at offloading different VPNs to different route reflectors. We looked at setting up static routes between PE and CE is one option. We looked at offloading all of the internet routes from the PE over onto the P router, so the PEs don't have to actually maintain an internet routing table as well as the VRF tables. And we looked at 3 ways of providing a VPN customer with internet access. And those 3 ways are that the customer has a direct connection from their CE site, doesn't go through the PE at all. The second way was that it does go through the PE, and we share routes between the VRF table and the main internet routing table to provide internet access. And the third way was that we have all of the internet traffic channeled through a particular customer site, and we just distribute a default route to that particular site. All right, so what we're going to do now is we'll take a break, and then we're going to do a lab on this, and the lab will involve us using a route reflector. So we'll take a look at that, and we'll set up our peering with a route reflector, and we'll implement a layer 3 VPN between multiple customer sites across the service provider core. So we'll get into that lab. We'll take a break, and then we'll come back and get into that lab.